Lecture 3.6, Probability Density and Mass Functions. Consider an experiment that measures a random variable. We can plot the relative frequency of the measurand landing in different bins, ranges of values, right? This is called a frequency distribution or a probability mass function. Consider, for instance, a probability mass function as plotted in figure 3.3. Like this. Where a frequency, AI, can be interpreted as an estimate of the probability of the measurand being in the ith interval. The sum of the frequencies must be unity. So if we take the sum of I equals 1 to k, where k is the number of bins of the frequencies, AI, we have to have them all equal 1, just like we knew last time, because we know how probability works already. We're just reviewing a little bit, but that's okay. The frequency density distribution is similar to the frequency distribution, but with AI being mapped to AI divided by delta x, the width of the bin. Okay. In this case, the delta x, typically you would take your bins to have fixed width, so your delta x would always be the same. If you wanted to get wild, you could have variable width bins. Might give you some issues. If we let the bin width approach 0, we're going to have them all be the same bin width. We derive the probability density function, which is if you take the number of bins to infinity and you take the bin width to 0, you get the probability density function, or PDF. We typically think of a probability density function f, like the one in figure 3.4, as a function that can be integrated over to find the probability of the random variable measurand being in an interval from a to b. So if we look at this, we have some measurand. We can have values of the PDF that are greater than 1 as long as the integral of the entire thing is 1. Okay. It can never be negative, though. And that's because if it was negative, if you integrated over that little bit and you got a negative probability coming out, that would be meaningless, right? We don't have negative probabilities. So this is our probability density function. This is our probability of being of this random variable taking on a value between a and b, the area underneath that curve between a and b. So that's what we've done here with this integration. Okay. Note that, like we mentioned, but I'll state it explicitly, the probability of x taking on a value in the interval from negative infinity to positive infinity is the integral from negative infinity to positive infinity of the PDF f of, and then we'll just use as a dummy variable of integration, chi d chi, and that has to equal 1. We now consider a common PMF and a common PDF. So we'll do a PMF first, the binomial PMF, and then we'll do a PDF. There are several of these that are common. Often we'll use a sort of standard set of them to model different real-world situations. This one is, so I'm only going to talk about ones that are useful to us. So the binomial one is one that's useful to us, so we'll talk about it. Consider a random binary sequence of length n. No, not you, Siri. Of length n, such that each element is a random 0 or 1, generated independently, like the sequence 1 0 1 1 0, etc. 1 1. Let events 1 and 0 be mutually exclusive and exhaustive, and let the probability of a 1 be p. Probability of the sequence above occurring is, so probability of getting the sequence 1 0 1 1 0 1 1 is equal to they're independent events, right? And they're mutually exclusive, so, and exhaustive. So we have p being the probability of getting that first one, then 1 minus p being the probability of getting that 0, second 0, and then p being the probability of getting the next one, and then p being the probability of getting the next one, and then 1 minus p being the probability of getting the 0, etc., down to ends with a 1 and a 1. There are n choose k possible combinations of k1s for n bits. So you guys have probably all seen the choose function. So n choose k, using the factorial there. Possible combinations of k1s for n bits. Therefore, the probability of any combination of k1s in a series is this f of k. So n choose k times the probability to the kth, so k1s happening, and then there have to be n minus k zeros then. So that's the probability of there being a given sequence of ones, or a given sequence that includes k1s. We call this the binomial distribution PDF. Okay. Let's look at an example. Consider a field sensor that fails for a given measurement with probability p. So we're taking that to be outcome 1, right? Fails, outcome 1. Given n measurements, plot the binomial PMF as a function of k failed measurements for a few different probabilities of failure. So if the probability of failure is 4%, 25%, 50%, 75%, or 96%, we want to know how many failures, or what is the probability of getting k failures in a given set of n measurements. So for different failure rates, we're going to have different distributions, right? So this is what we get when we do we use that probability mass function equation, just directly apply it to this problem using outcome 1 to be a failure. And what we get is for 4% chance of a probability of having a failure at any given measurement, we would see a distribution like this. So we expect that if there's only 4% of probability of getting a failure, your probability of getting no failures, or 1 failure, or 2 failures, or 3 failures, etc., pretty high. Okay, it's a low chance. Out of 100 different tests, you're probably going to end up with somewhere down in this range here. So like, it's very, very unlikely you're going to get 8 or 9 or 10 failures when you out of 100 when you have only 4% chance of getting a single failure in any one measurement. And then if you say, okay, if 25% failure rate, this is the distribution you see. For a 50% failure rate, this is the distribution you see. And of course, these are going to have peaks that happen around the probability, right? So when you have a 50% probability of failing on any one given measurement, then you have a very, your highest probability happens at 50%, okay? So that's the most likely outcome, is that half of your tests will fail. But there's also a pretty good probability that's going to be like 52, 55, 56, 57, whatever. Those are pretty common and are pretty likely, and so are the high 40s. Those are also pretty likely. So this is useful to us because we have this like pass-fail thing, and then like how many can you expect, or like you could start talking about confidence intervals and like having a certain confidence in having it be in a given range of failures, that type of thing. Yeah.
So for this problem, you mean that from the manufacturer, they said the sensor is having this rate of success like 95, 96%.
Yeah.
So then the failure rate is 4%.
Yeah.
In this case. So when we are taking the sensor from the drawer, so we're using that one.
Yeah. So we're expecting, if it's got a 4% failure rate, we're expecting it to be more like this distribution. If we're going to do 100 measurements, we would expect, if we were to plot them out, that we would be somewhere in here. If we were going to take the number of failures out of 100, it should show up somewhere in here. If we were going to take a bunch of samples of this, like 100, and then measure how many failures came out, and then we measured another 100, found out how many failures came out of that, and then measure another 100, how many failures came out of that, and we kept doing that, we would expect that if we plotted the frequency distribution of those occurrences, that it would look something like this. Yeah. Okay. So that's the binomial probability mass function. Useful one. And then you knew this one was coming, the Gaussian PDF. So the Gaussian, or normal random variable x, has PDF here. So if you've got a random variable x, you subtract out this value that we call the mean of x, and we square that difference, and we divide it by 2 times what we call the standard deviation. Oh, this is sigma squared, is the standard deviation of x. We call it standard deviation. We'll talk more about mean and standard deviation. For now, they're just defined by this definition here. It's just a constant you put in there, right? And, oh, by the way, this is the MATLAB script that generated that figure, the binomial figure, if you're interested. I gave you the MATLAB script. Oh, sigma is the standard deviation, sorry. Sigma is the standard deviation of x, and then sigma squared is the variance of x. Yeah, so that was actually correct. Very good. Consider the bell-shaped Gaussian PDF in figure 3.7. This one here. It is always symmetric. The mean, mu, is its central value, and the standard deviation, sigma, is directly related to its width. We will continue to explore the Gaussian distribution in the following lectures, especially lecture 4.3. But it's worthwhile getting a sort of sense of this. This is actually the same form that we used in the example with the Johnson-Nyquist noise, right? Okay, so it's Gaussian. Okay, so that's the Gaussian. We'll talk about so you guys will do problems where you have to find what is the probability of a Gaussian random variable being between this, and that. And you guys have to take those integrals. Now, integrating the Gaussian is actually challenging. So we will often just use tables to look up the integrals, and there are such tables that show up in the Kreisig textbook, so you can use those tables to do the computations. Okay? Any questions on just generally PDFs and PMFs? We'll talk about some more of them.